This week we'll talk about entanglement in many-body ground states. We have 5 lectures. The first one will be today on basics of entanglement, just defining background material. And then I didn't bring my laptop. It's good news. We won't be doing Julia today. But we will, for the second and third, so this one, lectures will be using Julia. And also, so in the second lecture, we'll be computing entanglement in the ground state of quantum spin chains. We'll have a little trick that will allow us to go from, instead of being restricted to 10 spins, we'll go all the way to 20. In the third lecture, we'll talk about entanglement in free fermion systems. We'll learn how to extract it, how to compute it. So that will also have a Julia component. And then there will be tutorial 3 and tutorial 4 on Thursday, which will be applications of this theory. And so they will also have Julia. And finally, the homework will also have Julia. But today and Thursday and Friday, we'll have 3 lectures without Julia. And then that's it. Next week, we'll probably not have to use Julia anymore. All right, so I hope you received my email. You should be installing additional packages for this week, and we will need that for tomorrow, so make sure that it's ready for tomorrow. All right, so let's start today with some preliminaries. You all know this, but I'm trying to introduce the notation I'll be using. So we'll be considering if we had an L-level system in quantum mechanics that's described by some complex vector space, which is Cn. And we'll use 1, 2, 3, all the way to n in CAD notation to denote an orthonormal basis. In this vector space. Good. And so a generic state, psi, in this Hilbert space can be written in that basis in this way. Okay, very good. No surprises there. For the case n equal to 2, we often talk about a qubit, or we may be talking about spin 1/2 degree of freedom, or maybe a fermionic mode, or a pair of Majorana. And sometimes we introduce some other notation for the basis. For instance, for a qubit, it is frequent. We may sometimes use 0 and 1 for the spin 1/2, up and down, and so on. Okay? Very good. And I'll be using more and more this week, and especially next week, a diagrammatical notation to denote tensors and vectors and matrices. So this A is a vector. So I may represent it by a circle with a leg which represents the index. And you'll see that so far that's not very important, but it will become more and more important later on. And this diagrammatic notation is something that is used in the context of tensor networks, but it's also very closely related to a notation introduced by Penrose. All right, so let's now consider, instead of one quantum system, suppose we have 2 quantum systems. Again, quantum mechanics tells us what we should be doing to describe such a system. So 2 such systems, A and B. Then we have that the vector space is a tensor product of individual vector spaces. And we can choose as an orthonormal basis just Ij, which I define as the tensor product of I in part A and J in part B. That's our orthonormal basis. So you've seen this. And so what does an arbitrary state look like here? Psi in this bipartite space is going to be sum over I and j of aij, ij. And in our diagrammatic notation, that's going to be represented, this tensor here with two indices is going to be A with two legs, I and j. All right? Very good. So that was A, B, C. We'll be talking a lot about reduced density matrices. And so rho for part A, if the whole system is in a bipartite state psi, this is nothing but trace over B of psi psi. And then this is nothing but sum, this partial trace means take a basis on B and compute this quantity. Okay, and if you then, this is an operator, a linear map in the space A, so it's some matrix which will have some coefficients, rho A, ik, ia, kb, sorry, ia, and very good. Where these coefficients, so maybe we can even do that using our diagrammatic notation. So at this point, what we have is psi represented, so this projector onto the bipartite state psi represented by A and A star, j, k, L. Okay, we have something like this that represents this projector. And then what we want to do is we want to take the partial trace over B of psi psi. So that's going to be, take this object again. We have I, we have K, and now we make a sum over this index. Okay? So this sum is represented by connecting the two indices together. Okay. And what that means actually is that rho A ik is given by sum over m. Let's call this m. There's a sum over m, and then A im, A k m star. Okay. This is nothing but saying that rho k I is the result of contracting together these two objects. Okay, that's a diagrammatic expression of that equation. Okay, very good. So let's, with this in mind, are there questions? Yeah.
Shouldn't it be like sum over I and k, rho A, I, k, I, A, k?
Where are we?
There on the first line.
First line?
Right. On the right hand side.
Here?
Yeah, the next equality.
Well, your browser catch them up.
Now your matrix is explicitly diagonal. Yeah.
This one? Yeah.
I think so.
Thanks. My mistake. Is it wrong here? Yeah, I know. Yeah, thanks. Any other question? Okay, so then this is what? This is 5.2. Entanglement in bipartite systems. All right. So first, let's define what we mean by entangled state. So we are going to consider psi belonging to some bipartite system made of two pieces, A and B. And we're going to say that psi is a product state if psi can be written as the tensor product of a state for part A and a state for part B. And we'll say that it's an entangled state if it cannot be written in this way. Okay? And so let's consider some examples. So if I give you the state 1 times 1, which I also, so 1A times 1B, which I also call just 1, 1. Is that the product state, or is it an entangled state? Okay. So what about if I give you 1, 1 plus 2, 2? Is that a product state or an entangled state? You said entangled, right? Okay, good. What about this state?
Product state. It's a product state.
Why is it the product state?
1 and 1 plus 2. 1 times.
Because we can write it as in this way, right? Very good. So what about this one?
Product state.
The product state? Who said that?
I said.
Why is it the product state?
It's just the product state of two superpositions. 1, 2.
So it's a 1 plus 2 times 1 plus 2. Very good. So also product state. And now the big challenge. What about this one? No, I don't know, or no product?
No product.
Why is it not a product?
It's not be written as a product.
Because you cannot write it? What if somebody else can write it? Okay, so it's not so simple, right? I mean, the easy cases we can follow, but how do we prove that this guy is entangled, but how do we prove that? Okay, so we'll answer this in a minute. Oops. You go up, you go up. But before we answer, let me give you a couple of examples that have even their own name. So this is just a normalization. In quantum information, you may have already seen this guy, which we call it a maximal entangled state of 2 qubits, or EPR pair, or EBIT, or singlet state. It has many names, okay? That's an example of an entangled state. We'll see why we call it EBIT later on. And another state that appears quite often, which I may use this notation, but that's not too important, is this one. In two n-level systems, we have what we call a maximal entangled state. Of two n-level systems. And we'll be introducing some definitions of entanglement measures, for instance, and we'll be evaluating those measures on these two states and a product state all the time, just as examples. So it's good to keep those in mind. Very good. So now I want to understand how to systematically answer the question. If they give me a pure state of two systems, parts A and B, how to systematically answer the question whether that state is entangled or not. Okay, that's what I would like to be able to do. And to do that, oh, I don't need to do this. I'm going to talk about Schmidt decomposition on reduced density matrices. So Schmidt and I'll start by considering some general properties of matrices. So I'll start by saying that if you give me an m times n matrix, there is something called the singular value decomposition. Or SVD for short. Okay? And this is nothing but a way of writing A as the product of a unitary matrix U, a diagonal matrix S, and another unitary matrix U. So if matrix A is m times n, then this is going to be m times n. This is going to be m times n, and this is going to be n times n. So if you want, I can draw. I'm going to assume, for concreteness, assume m is smaller than n. Then this is going to look like a small matrix multiplied by a matrix which may have this form. Okay. So this is m times n. This is m times n, and this is n times n. And this matrix is going to be diagonal, and it will have some positive entries in the diagonal. So diagonal. And we are going to, let's see, so what do we have? I said U is unitary. It's identity. U daga is the identity on the vector space of n dimensions. Same thing for V is the identity on the vector space of n dimensions. And Si are non-negative, and they are called, this is what we call singular values. Okay? Okay, so it's a simple fact linear algebra that any matrix A can be written in this way. Okay? Very good. So why are we talking about this? Well, let me also introduce, this was singular value decomposition. Now I want to introduce another decomposition. That's going to be the eigenvalue decomposition. Or eigenvalue decomposition. So given a generic matrix A, which was m times n, and for which we just wrote the singular value decomposition, we can produce two positive defined matrices by considering A times A daga, but also by considering A daga times A. Now, this matrix here is m times n, n times n. So this is m times n, okay? And this is n times n, okay, by construction. So these matrices have different size. But they have in common that by construction they are positive defined, which means that they can be diagonalized and all the eigenvalues are non-negative. Okay, so now what I would like to do is I would like to relate the singular value decomposition of matrix A with the eigenvalue decomposition of AA dagger, and also with the eigenvalue decomposition of A dagger A. All right? So this, we said that this one had singular value decomposition given by U as the dagger. So it follows that, let's write A dagger by using the singular value decomposition. That's nothing but U as V dagger. And now, right, this is the first one. And now we have V S dagger, U dagger, right? Very good. So now I look at this expression, I see V dagger V, that was identity. So I can remove it. I get U, S dagger, U dagger, okay? And I'm going to simply define this thing as some diagonal matrix S dagger. Remember, S is diagonal, so S dagger is also diagonal. And so this is U, diagonal U dagger, where D is nothing but, what did we call that, S? Yeah. S1 square, S2 square, Sm square. Okay? And this is already the eigenvalue decomposition of AA dagger. Eigenvalue decomposition. Okay? An eigenvalue decomposition of a Hermitian matrix is precisely one that is of the form unitary, diagonal matrix, unitary dagger. Okay? So if we know the singular value decomposition of matrix A, we know the eigenvalue decomposition of AA dagger. Very good. But we could also do the same down here. We could ask what's the eigenvalue decomposition of A dagger A. And what we have is, well, let's write a similar thing. So A dagger is V S dagger, U dagger. A is U S V dagger. Okay? Again, U dagger and U cancel, so we get V S dagger S V dagger. And now if I define this as D tilde, then this is nothing but V D tilde V dagger, which is again this eigenvalue decomposition of A dagger A. Okay? Now this time D tilde looks like this. It's an n times n matrix, which has S1 squared, S2 squared, Sm squared, and then zeros. Okay? Very good. So what do we want to learn from here? This will be closely connected to the decomposition of an entangled state. We'll see it in a second, but these are just simple facts of linear algebra. And the first thing we want to see is that the eigenvalues of A dagger and the eigenvalues of A dagger A, they are the same, the non-zero ones at least. Okay? So they share, they're given by S1 squared, S2 squared. These are the singular values of A squared. Okay? Very good. Any questions? So now I'm going to use this to find ways of understanding when a pure state is entangled or not. So all we need to do is we need to take our state psi, which in general can be expanded as Aij, I, and j. Okay, that's the most general expression for a bipartite state. And here what we're going to do is we're going to use the singular value decomposition of this tensor. This tensor has two indices, so we can think of this as a matrix, and we can singular value decompose this matrix. And in components, it's going to read like this. Sum over k, I, k. Remember that the singular value matrix was diagonal, and V daga kj. Okay, so this is just the same expression that we had up here. Okay, but just in components. So let me then rearrange this expression here. I'm going to replace A with the singular value decomposition, and then I can make first the sum over k, as k. Then we'll have sum over I. That's going to look like this. So there will be some sum over u of vectors I. So u, I, k are the coefficients. And then sum over j and matrix V daga. Okay, so I've not done anything magic here. I just replaced. Once somebody give me a bipartite state, I can take the matrix of coefficients in a product basis, and I can singular value decompose it, and automatically I can rearrange this state in this way. And this, well, now I just start defining things however I find convenient. And this is sum over k. K only needs to go to n values, because there are only n different sk's which are non-zero. And this, I'm going to call it phi ka tensor phi b k also. Okay, so this thing here is just whatever this linear combination gives me for a fixed value of k. Okay, and the same here. This is nothing but this linear combination. You specify k, and then you have a sum over j. Right? This thing only depends on k, so I call it phi k. Okay, and this is what we are going to call. Sorry, and look at this. This was an orthonormal basis. We said from the beginning that this denoted an orthonormal basis. And now we take linear combinations, but with coefficients given by the entries of a unitary matrix. So the resulting set, this is also an orthonormal set. Okay, meaning phi ka, phi k prime a is delta k prime. Okay. This, if you compute this scalar product, you'll just find the unitary entries, which are orthonormal by construction. And the same thing here. This is also an orthonormal set. Very good. And remember that Sk are non-negative. And this is what we're going to call the Schmidt decomposition. And so now we can answer the question that we had before. If they give you some bipartite state, say this one, you just, that one corresponds to some matrix A, which would be of the form 1, 1, 1, minus 1, something like that. Okay. Now you singular value decompose it, and you look at how many singular values it has. If it has just one singular value, we have a product state. If it has more than one singular value, non-zero singular value, it's a product. It's not a product state. It's an entangled state. Okay? So we have an answer to that question. Yes?
Is the singular value decomposition unique after reordering of the elements?
Right. It's pretty much unique, but it's not unique. So there is the singular values themselves are unique. Okay? But the unitaries that you put the u and v do not need to be, they are not unique. You can, basically, this is a diagonal matrix. This is a diagonal matrix. So I could introduce here some other diagonal matrix made of, with complex spaces in the diagonal, and also another one here. So V daga is the identity, so I can put it in here. I can commute this with S, right? And I can multiply these two together and these two together, and this will give me a new pair U tilde and V tilde daga. with the same singular values, but I have a new decomposition. Okay? So it's not completely unique. Yes?
Do these singular values relate easily to eigenvalues? Or?
Yes, we're going to see that in a second. Well, actually, we saw it before, right? But I'm going to relate it now to the reduced density metrics. But we said that, right? That the eigenvalues of A dagger A and A dagger were the square of the singular values of A. Okay, so we have this. We know how to find out whether, systematically, whether a bipartite pure state is entangled or not.
Like, is it possible that, like, in case of singular value decomposition, like with this scheme, like we find that the psi can be written as non-product state, but what if there is some more clever way to reorganize everything to write it down as a product state? Like, how does theorem there?
So now we have a if and only if. So if the singular value decomposition only has one non-zero singular value, okay, then automatically this expansion here gives you a product state. Right? And if you had the product state, if your state is a product state, okay, it can be written in this way with a single term. So since the singular values are unique, okay, this is an if and only if. Right? The information we care about in the end is the set of singular values. We count how many singular values are non-zero. If it's just one, then it's a product state. And it's an if and only if statement. Very good. So we're happy. What did I want to say? OK, and then also, well, we had it somewhere, row A. We can compute row A. It's here. Have row A. But if you look at that, that looks like AA dagger. So indeed, now what we also have that row A, the reduced density matrix for part A, so trace over B of psi psi, okay, is equal to, well, let's take the trace precisely using this basis on B. We can take the trace on B using whatever basis we want. Let's choose the Schmidt basis, the one that appears in the Schmidt decomposition. So sum over K phi B K psi psi phi BK. Okay. But now if we use this expression for psi, ket, and bra, it's just one step to see that this becomes single value square phi K A phi K A. But this shouldn't surprise you, because this is the eigenvalue decomposition. Remember, this is nothing but, what did we say it was? AA dagger. And this is nothing but U S dagger S U dagger. Okay? So what we're seeing is that the Schmidt coefficients that we wanted appear as the eigenvalues of the reduced density matrix. Okay? So we can do the same for row B, but this is the same as A dagger A before. That would be trace over A. And yes, I should choose the notation more carefully and not involve. This A has nothing to do with this A. Okay, this is a matrix. This is part A. Next year. Okay. Sum over K, and then, well, I choose here phi A K. Same thing. What do I get? SK squared phi B K phi B. Okay, so what we see, and this is the eigenvalue decomposition of row B. Okay, so what do we see? We see that we had a bipartite state psi. We have a Schmidt decomposition, which allows us to decide whether this state is entangled or not. And there is a close relation between the Schmidt decomposition and the eigenvalue decompositions of the reduced density matrices for part A and for part B. Okay? And the relation, let me highlight it, is as follows. Singular values appear here squared, both in row A and row B, as the eigenvalues of row A and row B. So another way you have to decide whether a pure state is entangled is you compute the reduced density matrix, you eigenvalue decompose, so you get the eigenvalues of the density matrix, and see how many eigenvalues are different from 0. If you have one eigenvalue, only one eigenvalue that is different from 0, it means you started with a product state. If you have more than one eigenvalue that is different from 0, then you started with an entangled state. Okay? You can either look at the Schmidt decomposition, or you can look at the reduced density matrices and extract the same information. Now, what other relation we have between the Schmidt decomposition and this decomposition? Well, look at these guys. The Schmidt vectors, the ones that appear in the Schmidt decomposition, are the eigenvectors of the reduced density matrices. This one, for part A, and the same for part B. Okay? And in particular, we've seen also that the non-zero eigenvalues of row A are the same as the non-zero eigenvalues of row B. Okay? Good. So maybe I should have to write this. Non-zero eigenvalues of row A equal to non-zero eigenvalues of row B. Okay, and these are given by singular values square. So let's go to our examples. So if we had a product state, then instead of saying the number of single values that are non-zero is equal to 1, I'm going to say the Schmidt rank, okay? Schmidt rank is equal to 1. Chi equal to 1, that's Schmidt rank. And that's the number of non-zero singular values, equivalently the number of non-zero eigenvalues in row A or row B. Okay? So in terms of the eigenvalues P1, let me find this here. So let me call these guys Pk. These are the eigenvalues of the non-zero eigenvalues of the reduced density matrices. So here, vector P would be 1, 0, 0, 0. Okay? Another example, well, we said we had this singlet state. Okay? And so what we can do with this singlet state is you go through this process, you realize this is already the Schmidt decomposition because this guy here and this are orthonormal for part A, and also 0 and the 1 are orthonormal. So this is already in the Schmidt decomposition form. It has, therefore, 2 terms. And if we look at the vector of probabilities for the reduced density matrices, they are of this form. Okay? 1 half, 1 half, 0, 0, 0.
So
Yep.
what is the exact definition of the Schmidt rank?
The Schmidt rank is the number of non-zero singular values. All right. Our third example was this state that was maximally entangled. in a maximal entangled state of two n-level systems. And what's the Schmidt rank for this guy?
N.
Why is it n?
Jordan Schmidt basis.
Because this, indeed, because this is already written in a way that you have an orthonormal set of states for part A and an orthonormal set of states, 1 to n, for part B. Okay? So it's already in the form of a Schmidt decomposition, and we see that there are n terms. And the corresponding probabilities look like this: 1 over n, 1 over n, 1 over n, n times. Okay? Okay, so we can go to the next. Other questions? Yeah.
In case the second example, can we, like you said, it is already Schmidt decomposed form, but isn't that when we Schmidt decompose the psi, the coefficient should be always positive, like singular values are always.
Oh, you're right. You're right. So we'll have to take and say, oh, this guy here,
yeah.
the 0 in part A. Okay, we'll attach the minus sign to it, and that will be part of the vector, and then the singular value is going to be 1 over the square root of 2. Yeah, good point. So this is not the Schmidt decomposition, but it's very close to.
Yeah,
you can already see that there is orthonormality between the base vectors of part A that you are using and vectors of part B. And so all you need to do is to get rid of this minus sign. But you're right. This is, strictly speaking, not yet the Schmidt decomposition. All right. So now, I don't know what I want to use. Maybe this. So let's talk about measures of entanglement. That's 5.3, I guess. So far we have understood, if they give you a pure state of part A and B, you have understood how to find out whether it's entangled or it's a product state. But it turns out that within entangled states, there are many types of entangled states, and we would like to be able to quantify how entangled, how different from a product state they are. Okay? And we just said, or maybe the first thing to say about this is that given psi, or bipartite psi, it's actually the Schmidt coefficients, which I'm going to denote as square root of the eigenvalues of the reduced density matrix. So these Schmidt coefficients are what we would call a complete characterization of the entanglement properties of this state. Okay? Or anything that you want to ask about how entangled this state should be a function only of the Schmidt coefficients. Why is that? Well, what we can do is, what we're doing here is we're taking the vector space of the bipartite system. Okay? We're looking at two states, and what we know about entanglement is that it does not depend on, we can change bases on part A and part B without changing how entangled the state is, right? If it's a product state, if you change bases in part A and part B, it's still a product state. So we'll take this as a definition. We're going to identify any two states that are related by changes of bases in part A and part B. So a change of basis corresponds to a unitary transformation on part A and another on part B. And what we are taking is, what we're saying is, we say psi is equivalent to psi prime if psi prime can be written as acting with a unitary on part A times a unitary on part B, some unitary on part B. Okay, we say that these two states have the same amount of entanglement. Okay, if we can relate them by just changing bases on part A and part B independently. Very good. And the only thing that is left from psi, if psi was some is a state that is represented with a matrix A, then this will come with a matrix A prime. And the relation between the two is the only thing that remains stable here is precisely the singular values of matrix A. Okay? So that's the Schmidt coefficients. So the Schmidt coefficients label the different equivalence classes that we have in a space of two systems when we identify states by local changes of basis. Very good. So that's nice. We have these Schmidt coefficients. We've identified that these are the ones that completely characterize the entanglement of the state. But this, in practice, this doesn't seem very, maybe it's useful, but it's not very practical. We would like to be able to just go by, say, one number. Give me a number that tells me about how entangled this state is. Of course, collapsing a collection of numbers into a single number implies losing information. But sometimes it's OK to just not be so precise and just be able to give a concrete answer. So, for instance, we would like to give a single number, okay? A single number, not the full set of Schmidt coefficients. And so we would like to find some quantity, epsilon of psi, which is a single number. And of course, which tells us something about the entanglement. Okay? And we just said that this, so what do we know? We know that E of psi should be equal to, should be just some function of the Schmidt coefficients. Okay? We said that the entanglement is completely characterized by the Schmidt coefficient, so whatever quantity we decide to use to measure entanglement should be only a function of the Schmidt coefficients. It's reasonable to ask that this quantity should be 0 if and only if psi is a product state. So that when I measure this quantity, when I evaluate this quantity on my state, if it's 0, okay, I know it's a product state. If it's not 0, I know it's entangled. Okay? These are requirements that we can decide, we can agree. We agree on them, then we can move forward. And the other thing we want to do is, there is this idea that entanglement, whatever it is, it's something that cannot be increased if you manipulate your bipartite state with something that is called local operations and classical communication. And if you took some quantum information lectures, maybe that was described. If not, too bad. But what we say is that under local operations and classical communication, a set of transformations that you allow on part A and part B independently, and also you allow some correlation between what you do on part A. So part A, I make a measurement, I tell part B, hey, I just made a measurement and I got the result. And then part B, depending on that, they can make their own manipulations back and forth. So if a state psi can be transformed into state psi prime under local operations and classical communication, then it's natural to demand that psi, that this quantity on psi be, that this quantity does not increase in the process, right? If we're trying to measure entanglement, characterize how much entanglement we have, and we have this process that we agree that cannot create entanglement, then we'll demand this condition, which is called monotonicity, under LOCC, okay? And so these properties, and maybe a few others that we won't discuss, define what's an entanglement monotone, and we're going to use this entanglement monotone, this quantity that can only decrease when we manipulate our system locally. We'll use them to measure, as a measure of how much entanglement we have. And so let me give you an example. First example we'll consider is precisely the Schmidt rank. Okay, the number of non-zero singular values in the singular value decomposition. So you can see that, oh, sorry, the log of the Schmidt rank. Okay, so remember it's a product state. If it's a product state, a state is a product state if and only if chi is equal to 1, so the logarithm is going to go to 0, right? This condition. It's only a function of the Schmidt coefficients. It only counts how many are non-zero. And you can show actually that under LOCC, the logarithm of the Schmidt rank can only go down. It cannot increase. Very good. So we could come up with many, many different quantities, many other examples, but I'm going to directly focus on the one that is used mostly. And this is going to be the entanglement entropy. Okay? It's an example of an entanglement monotone. So the second example, entanglement entropy. And it's the one that we'll be using mostly during the week. And so simply, you give me psi. Well, first, what's the von Neumann entropy? Von Neumann entropy of a density matrix is given by minus the trace of rho log rho. And here in quantum information, or coming from quantum information, what we do is we put base 2, log 2, okay? And that's something that may seriously impact the result of any calculation, so keep in mind this. And that's nothing but minus sum over the eigenvalues of rho okay, and so the entanglement entropy is nothing but you give me psi, I compute rho A or rho B, since the eigenvalues of rho A and rho B are the same, and then I attach the von Neumann entropy of rho A. I use this as a measure of entanglement for psi, okay? And that again, well, let's see how much it is. So examples, let's compute this in particular examples. And first we have our product state. How much is the entanglement entropy for a product state? Yay. So we have P is 1, 0, 0, etc. And therefore, the entropy of rho A, which is this sum here, is minus 0 log to 0 minus, no, first 1, 1, 1, minus 0 log to 0. And this one here gives us a 0 because of the log of 1, and this gives us a 0 because of that. And we get 0. Okay, so we're happy, fulfills one of the requirements, and you can see that one can show that it also fulfills the rest. In particular, that it only decreases under local operations from classical communication. So another example then would be for our singlet state. And in this case, remember that we had a vector of probabilities which was 1/2, 1/2, 0, 0, 0. And then if we compute the entropy in this case, we get minus 1/2 log 2 of 2. But we get two contributions like that, so times 2. And then the rest are zeros. So, sorry?
Log 1/2.
Yeah, that would work better. That's right, thanks. And so what we have, is that correct now?
Yep.
Minus log of 1/2. But this is nothing but the log 2 of 2. and this is nothing but 1. And this is why we say that this has one e-bit, entangled bit of information. Okay, this state, a singlet, has 1 bit or 1 entangled bit of entanglement, 1 bit of entanglement or 1 e-bit. Okay, and what's our other favorite example? We have this guy, the maximally entangled state of 2 n-level systems. And now we compute this entropy. And we find that it's a minus 1/2 log of 1/2. And this, we have it, why am I writing this? 1 over n. Oh, that's because I didn't write the vector. 1 over n, 1 over n, 1 over n. So we have this, we have it n times, right? And so this is nothing, but this n cancels this one, and this minus sign, I use it to flip to this log 2 of n, okay? And that's how much entropy we can actually have for any possible probability distribution on n elements. That's the maximum amount of allowed entropy. This is the probability distribution that maximizes the entropy. We just have n different, a vector of n probabilities. Okay, that's why we call it maximally entangled, because it has the maximum amount of entropy. Very good. So I could define the Renyi entropies, but yeah, let me just mention that there are other examples that you can find in the literature, and one of them, another example of measure would be the Renyi entropy. Which is defined with an index alpha, also in terms of the reduced density metrics for part A, and it's given by this expression instead. So you take rho, the reduced density metrics, to the alpha power, take the trace, take the log, and divide by 1 minus alpha, and this is the same as doing the same thing with the eigenvalues. Okay, and this one is also, well, this for each value of alpha 0 to infinity, for each value of alpha you have a different measure of entanglement, and for alpha going to 1, one can show that in the limit when alpha goes to 1, this becomes the von Neumann entropy. Okay? So it's von Neumann entropy is one guy in this family. There is another interesting limit, which is when alpha goes to 0, then this becomes the logarithm of the Schmidt rank. So this family of Renyi entropies contain the entanglement entropy for alpha equal to 1, and the Schmidt rank, the log of the Schmidt rank for alpha equal to 0.
What is the benefit of calculating the piece instead of just calculating the entanglement?
The benefit?
Yeah.
Sometimes it might be much easier, because it's easier to take rho to some power. Say in quantum field theory, these calculations are done, and people know how to take a power of rho using something called the replica trick. Whereas if you were to have to compute the logarithm of rho, that's much more complicated. Actually, the way to compute the entropy in that case, the von Neumann entropy, is by computing the Renyi entropy for integer alpha, and then assuming that you compute it for integer alpha and assume that the expression that you get does not rely on alpha being integer, and then you take the limit, alpha going to 1. Okay? Very good. So I wanted to finish on time, and I almost succeeded, so I'll leave it here.